Hello, this is Dr. Bob Brown. This is the first section of our pre-calculus course, section 5.1, and we're going to be talking about polynomial functions and their models. This gives you an idea of some of the things we're going to be talking about. First of all, we're going to be able to identify polynomial functions and their degree. I suppose you probably already have a feel for this because you studied some polynomials in college algebra. Then we're going to place a great deal of emphasis on graphing polynomial functions, but we're not going to rely on transformations. We're going to use a graphing calculator. And in this case, I would encourage you to use an equivalent TI-83, 84, or the plus models of these calculators. Then we're going to be able to identify the real zeros of a polynomial function. And then we're going to get even further into polynomials by being able to analyze the graph. And then very briefly, we're going to talk about how we can build cubic models from data. So first of all, identifying polynomial functions and their degree. I'm sure you've seen this before. Here's a general form of a polynomial function. F of x equals a sub n, x to the n, a sub n minus 1, x to the n minus 1, all the way down to a constant terms, a0. A sub n, a sub n minus 1 are called the coefficients of the polynomial. N is always more than or equal to 0 and is an integer. And of course, x is a variable. You should know that the domain of a polynomial function is a set of all real numbers. Remember, the domain are the values that x can have. In this case, it's all real numbers between minus infinity and plus infinity. Now let's look at these functions here. Each of these is a function. Some of them are p of x, f of x, g of x, h of x. Notice it doesn't really matter what you call them as long as you use some correct notation. We're going to look at each one of these and decide whether it is a polynomial. Notice this polynomial is of degree 3 because that's the highest exponent you see. You don't see any exponents that are not integers. It does have a constant term, minus 9. That would just be minus 9x to the 0 power. Of course, x to the 0 power is 1, so that's minus 9. So the leading coefficient is 5x cubed, and the constant term is minus 9. The next one, it's not written with the highest exponent term first, but this is okay. Notice that this is a polynomial, but you need to look at all the terms and see that it's of degree 4. You could write it in standard form like this. And the leading term is minus 3x to the 4th, and the constant term is 2. Now, the first thing you notice about function c is that it is equal to x to the 1/2. And 1/2, of course, is not an integer, so it's not a polynomial. For d, notice that it is a ratio of polynomials, which is a rational function, but not a polynomial. Notice you're not being able to write this as a sub n x to the n plus a sub n minus 1 x to the n minus 1 and so forth. It's a ratio of two polynomials. By the way, this function is a rational function, which is a ratio of two polynomials. Number E looks very simple. G of x is equal to 8. Well, that is 8x to the 0 power equal 8. It's a constant term. It's of degree 0. And it's in standard form. And it's a very simple constant function. H is a product of minus 2x cubed times x minus 1 squared. Notice that if you multiply this out, x minus 1 squared is x squared minus 2x plus 1. And if you multiply that out, you get this. And you can very quickly see that every term is going to be x to some n power. And in this particular case, it's a fifth order polynomial. Notice you don't have to multiply it out to know what the order is. You can just say this is going to be minus 2x cubed. And the highest term in this expression is going to be x squared. So you can go ahead and figure out that the leading term is going to be minus 2x to the 5th without multiplying everything out. That could save you a little bit of time. Now, we're going to look at how you can identify a graph as possibly being a polynomial function. First of all, the graph of a polynomial function is always smooth. It's always continuous. And in fact, it's a nice looking function to look at. If the function is not smooth, in fact, suppose it has a corner, a sharp corner, or a cusp, or a very pointed edge, or if it has a gap in the function, or a jump from one point to the next and is not connected, or if there is a hole in the function, that a hole is where a point that does not exist in the function, then it cannot be the graph of a polynomial function. Now, I'm just going to insert a little note here. Just because a graph is smooth like this doesn't necessarily mean that it's polynomial. It just means it could be a polynomial. I'm sure that some of you have seen a graph that looks like this, a sine wave. That's a smooth function, just as smooth as it can be. but it's a sine function and not polynomial. In fact, later on in this course, we will be graphing trigonometric functions like sine, cosine, and tangent. Now, just a slight definition here. Here we're going to talk about a power function of degree n, and it's just simply written f of x equal a x to the n. In other words, it's just x to a power. N is more than 0. A is non-zero. If a were 0, it would just be the 0 function. This is called a power function, and we will find out that sometimes the way that polynomials behave as x goes to infinity or x goes to minus infinity can be represented by a power function, which turns out to be the term of highest degree. And it tells you what the behavior of the function is to the left and to the right. Here are some examples of power functions. First one here is y equal x squared, and it's just a simple parabola. If n is even and larger than 2, then you will find out that the function will get steeper and steeper. In fact, look at x to the 4th, it's getting pretty steep. And x to the 8th, which is a blue function, it's getting very steep. Notice that f of x equal x to the n, when n is even, will always go through the point minus 1 and 1 and plus 1 and 1. That's because 1 to the n, when n is more than 0, is always 1. And if minus 1 to the n, if n is even, you're going to always be positive. Now, here is just some examples of table of power functions with the power functions getting pretty large. Notice if you take a power function and you insert a number less than 1, that end result, the function can get very, very small. I want you to look at the calculator here. For instance, we're going to put, let's put 0.3 in for x to the 20th power. So let's do 0.3. Looks like I need to turn the power on. 0.3 to the 20th power. Hit enter, and notice we get 3.48679. If you round off to the nearest thousandths, you get 3.487 times 10 to the minus 11. You need to remember how to read your calculator scientific notation. And you can just maybe pause for a second and check and see if you can do all of these others on your calculator. Here is a slide on the properties of power functions. Notice I didn't answer the phone there. Somebody's calling me pretty late here at night. but I will call him back later. Properties of power functions, f of x equal x to the n, where n is a positive even integer. If it's an even integer, then the function is an even function, and the graph is symmetric with respect to the x-axis. For instance, x squared looks like this. X to the fourth would look like this. X to the eighth would look like that, would be even steeper. As we said, it always contains a point minus 1 and 1, 0 and 0, and 1 and 1. As the exponent n increases, the graph is steeper. When x is less than minus 1 or x is more than 1. But for x near the origin, the graph tends to flatten out and lie closer to the x-axis. Here's some examples. Y1 equal x to the fourth, y2 equal x to the eighth, y3 equal x to the 12th. You can put all these in your calculator and see what this looks like. If you change the range from minus 1 to plus 1, you can see just how flat the function is around 0. And the larger the exponent, the steeper it is around x equal 1. You might try to put these in your calculator also, just to verify. Now, when f of x is a power function, x to the n, n is a positive odd integer, then it's not going to be symmetric with respect to the x-axis, but it will be symmetric with respect to the origin, and it will be an odd function. Odd means what you see on the left is the negative of what you see on the right. And I know you talked about odd functions back in college algebra. The domain and the range is a set of all real numbers. Notice that if n were even, the domain and range were, the domain is minus infinity to plus infinity, but y is more than or equal to 0 for n even. For n odd, the domain is still minus infinity to plus infinity, and the range, though, goes from minus infinity to plus infinity also. You can verify that the graph always contains a point minus 1 and minus 1, 0, 0, and 1, 1. Again, as n gets larger near the origin, the graph will begin to flatten out. And that can be verified by plugging in various values of n for x to the n. Here is x cubed. Here is x to the fifth, x to the ninth. Notice it flattens out as x gets close to 0. It gets very steep around x equal 1. Just some more examples. X to the 11th, x to the 7th, x cubed, always getting flat close to 0, getting steeper and steeper close to minus 1 and plus 1. Now we're going to graph polynomials But unlike the textbook talks about, we're not going to always use transformations. We're going to use your calculator. For instance, we're going to graph f of x equal 1 minus x to the fifth. I hope you already know how to use a graphing calculator, but I probably will make some videos on how to do more of this. Let's turn this one on, clear, hit y equal, and then insert the graph 1 minus x to the fifth power, and let's set up the window to equal the window we see on the result here, minus 2 to plus 2 for x min and x max, and minus 2 to plus 2 y min and y max, and hit graph. And notice we get exactly the same graph as shown here. Why use transformations if you can do it with a calculator? Now let's graph 1/2 times x minus 1 to the fourth power. That let's hit clear and use parentheses for our 1/2. 1 divided by 2, close parentheses, x minus 1 to the fourth power. Let me clear that again because I noticed there I'd left a 5 there. So let's do this again very quickly. 1/2 x minus 1 to the fourth power. And let's go ahead and hit graph. And that should be the answer. And sure enough, the solution is just like this. You can always check to see if the value at 0 is what it should be by hitting second calc, hitting 1 for value, putting in x equals 0, hitting enter, and you get 1/2. Let's go ahead and do that again. Second calc, value, x equal 1, y equals 0. Second calc, value, x equal 2, hit enter, and again y equal 1/2. So this verifies the graph that we have. Now, we're going to get a little bit further into analyzing a polynomial. We're going to learn how to identify the real zeros of a polynomial function and their multiplicity. First of all, look at a typical polynomial function, and this one is shows enough information to get across several different concepts. First of all, you want to look at what we call x-intercepts, where the function crosses the x-axis. You also notice that in one region it's above the x-axis. That's these two regions. In this region and this region, the graph is below the x-axis. And these will be zeros, and a zero, if x equal r is a zero, x minus r is a factor, and we're going to talk about the multiplicity of these zeros. If at a zero it crosses the x-axis going through, the multiplicity has to be odd. And if it just touches, the multiplicity is even. So the factor x minus r and n is a multiplicity, or m is a multiplicity. It is even if it just touches, and it is odd if it goes through. Now, just to go back to the definition of a real zero function, if f is a function and r is a real number, and f at r equals 0, then r is called a real zero of f. Now, you need to understand the following statements and that they are equivalent. If r is a real zero of polynomial function f, that's equivalent to saying that r is an x-intercept of the graph. It's also equivalent to saying that x minus r is a factor, and r is a solution to the equation f of x equals 0. Now, let us graph this function. Bring up the calculator. Clear it. F of x equals x cubed minus 4x squared minus 11x plus 30. Let's set up the window to be between minus 4 and, in this case, plus 6. And let y min be minus 50 and y max be plus 40. You hit graph, and sure enough we get the same function. We have minus 3 wait a minute. Let's look at this. X cubed minus 4x squared minus, notice we put it in minus 11x. It's not 11x. Always check what you're doing. X cubed minus 4x squared x cubed. Notice you have to go to the right here. Minus 4x squared minus 11x plus 30. And now, when we graph it, it should look exactly like this does. It goes through minus 3, and it goes through plus 2, and it goes through plus 5. Now, if x minus r to the mth power, where m is an integer, is a factor of a polynomial, and x minus r to the m plus 1 is not a factor, then r is called a zero multiplicity m. That means that if, for instance, x minus 10 to the 8th power is a factor, but x minus 10 to the 9th is not a factor, then 10 is a zero, a multiplicity 8. Now, let's graph this polynomial. In the process, we're going to find the x and the y intercepts. We're going to graph it with our calculator and not multiply all this out. Clearing out, we can put x plus 1 squared times parentheses x minus 2. And let's zoom to the standard window, which is zoom 6. And let's see what the graph looks like. The graph looks pretty good. You can zoom in on it, but you can already see that x equal minus 1 is a zero. Multiplicity 2, you can see, power 2, and x equal 2 is a zero of multiplicity 1. The y-intercept, you can get several ways. You can try to read it off the graph. It looks like it might be minus 2. We can calculate that by just doing second calc value, put in x equals 0, and sure enough you get the y-intercept is minus 2. So as we said, the y-intercept is minus 2. Plug in x equals 0. The x-intercepts can be determined by setting everything equal to 0 and just solving. And the graph also solved it for us. X plus 1 equals 0 means x equal minus 1. X minus 2 equals 0 means x equal 2 is a 0. And the next page is a graph just like we just created. Now, notice the zeros were at minus 1 and plus 2. So we can break the line up into 3 intervals, 1, 2, and 3. The first interval is minus infinity to minus 1. The second interval is minus 1 to 2. And the third interval is 2 to infinity. Looking at the graph, the first interval is below the x-axis. The second interval is below the x-axis, minus 1 to 2. And the third one is above the x-axis just by looking at the calculator. If we wanted to calculate the value of the function at minus 2, you can go second, calc, value, plug in minus 2, and notice you get minus 4, go second, calc, value, minus 1, hit enter, you get y. Excuse me, instead of putting in minus 1, the value is obviously 0. Let's put in the value 2. Or let's put in the value 1. And we get f of 1 equal minus 4. And if we put in the value 3, put in the value 3, we should get 16. Now, if the 0r is of even multiplicity, the sign of f of x does not change from one side of the graph to the other. So, if we have a 0 that looks like this, this would be a 0 of even multiplicity, that means the graph just touches the x-axis at x equal r. If r is a 0 of odd multiplicity, then the graph will cross the x-axis. And when you see that, you know that the 0 has to be odd multiplicity. One other theorem or one other definition, a turning point. If f is a polynomial of degree n, then the graph of f has at most n minus 1 turning points. If a graph has n minus 1 turning points, then degree must be at least n. So you can count turning points. For instance, this graph has 1, 2, 3 turning points. So the degree is at least 4. Now, we want to look at these 4 graphs and determine whether or not they could be a polynomial function. Look at the four and just think about them. We're going to examine all four of them on the next few slides. Number one, cannot be the graph of a polynomial because there's a hole here and there's a jump. Therefore, it is not a polynomial. Graph B, though, is nice and smooth. It has 3 zeros, and it has a y-intercept. It's smooth, and it has 1, 2 turning points. So the degree is at least 3. Now, this looks smooth up to a point, and then all of a sudden it takes off. So it is not cannot be the graph of a polynomial. D, however, is a very smooth curve. It has 2 zeros, a nice y-intercept. It has 1, 2, 3 turning points. So its degree at least 4. Now, this is a theorem you may have had in college algebra, and what it tells us about is what happens to the graph of a polynomial as x goes to infinity or x goes to minus infinity. In other words, how does it look on the far left or the far right? And it says for large values of x, either positive or negative, the graph of a polynomial function given here closely resembles just the leading term, a sub n, x to the n. It dominates. So if you want to know what the behavior of the function is on the left or the right, all you need to do is graph a to the n, x to the n. And if n is odd, it's going to be an odd function, either up to the right and then down to the left, or down to the right, or up to the right and down to the left. For instance, example, we plotted here a function, a cubic function, in red, and then we plotted minus 2x cubed. Notice that as x goes to infinity and minus infinity, the two graphs are going to look closer and closer like one another. And here is a table of f of x and minus 2x cubed for various values of x. If you plug in x equal 10, one is minus 2,000, the other is minus 1494, not very close. But if you plug in x equal 1,000, you get minus 2 billion, and then minus 1.994 billion, which are pretty darn close. In fact, if you gave me $2 billion, I wouldn't really mind the fact that there was about 5 million that you gave the other person here. Not really that much difference between the two. Now, we're going to ask a question here. Which of the graphs in this figure could be a graph of f of x, x to the fourth plus ax cubed plus bx squared minus 5x minus 6? What we're going to do is look at each one and see which ones could be it. And we're going to look at some of the things we know about, like number of turning points, the y-intercepts, etc., and see which ones could be the graph. Okay? First of all, let's look at the first one. It has a y-intercept. Is positive. Notice that f of 0 up here is minus 6. So that could not be the graph. Let's also look at the second one. Notice the y-intercept is negative. So that could go with a minus 6. And notice that we have 1, 2, 3 turning points, means the degree at least 4. So this could be. Let's see if C could be. Notice it's got a negative y-intercept, but it has 1, 2, 3, 4, 5 turning points and degree at least 6. So this one could not be. Now, notice that the end behavior is down and down on the right and the left, but the term x to the fourth, which determines that behavior, means it would be up on the right and up on the left. So this could not be. So the only one that could be is graph B. Now we want to write a polynomial function for a graph that we're given. So now we're given the graph and we want to write a polynomial function. And notice we have a 0 of x equal minus 2, which means that x plus 2 is a factor. And since it just touches, it's going to have an even multiplicity. And if you want to do it with the smallest degree possible, we'll make that a 2. Here's a 0. It goes through the x-axis. X equal 0 is a 0, so x to the 1 power would be a factor. It has to be odd, so it's either got to be 1, 3, 5, or 7, so make it the lowest factor would be x. Here we have x equal 2. So x minus 2 is a factor. And since it goes through, it's going to be a multiplicity that's odd, and so we'll pick 1. So now, putting all this together, we get the function of x is some constant a, which we have to find out, times x plus 2 squared times x minus 2. Now all that you have to do now is find out what a should be so that the point minus 1 and 6 is on the graph. So we put x equal minus 1 into the equation. So alpha minus 1 equals 6. So we put 6 equal a, minus 1 where the x goes, minus 1 where the x goes, that's minus 1 plus 2, and then minus 1 where the x goes, and you end up with 6 equals minus 1 times plus 1 times minus 3. So that is 3a. So a is equal to 2. So the function we're talking about is 2x times x plus 2 squared times x minus 2. Now, you can check it by graphing it, and indeed you will find it will be the graph that's shown here. Now, let's go ahead and analyze the graph of a polynomial function. Let's take the factored form of a polynomial function, 2x minus 1, 2x plus 1 times x plus 3 squared, and you can immediately begin to analyze it. The zeros are at 2x minus 1 equals 0, or x equal 1/2. 2x plus 1 equals 0. 2x equal minus 1, or x equal minus 1/2. So we have 1/2 minus 1/2, and then finally x plus 3 equals 0, and x equal minus 3 is a 0. This is a multiplicity 2, multiplicity 1, and multiplicity 1. So let's continue. You can multiply out all of these factors to see what the polynomial would be. 2x minus 1 times 2x plus 1, that gives you 4x squared minus 1 times x plus 3 squared is x squared plus 6x plus 9. Multiply all that out, and you will finally get this. Note that to graph this, you do not have to multiply it all out. We found already the x-intercepts, 1/2 minus 1/2, and x equal minus 3. So now looking at the zeros, plus or minus 1/2 and minus 3. The zeros at plus or minus 1/2 are zeros of multiplicity 1. So the graph crosses the x-axis at x equal minus 1/2 and x equal plus 1/2. The 0 minus 3 is a zero multiplicity 2. So the graph touches the x-axis at x equal minus 3. The turning points, notice that the degree is, this would be x squared, this would be x times x, so it would look like 4 x to the 4th. So the degree is 4, so the turning points would equal 3. So as we just analyzed, the maximum number of turning points would be 3. Then we will plot the graph, and notice it does have 3 turning points. It just touches at x equal minus 3 and goes through at x equal minus 1/2 and plus 1/2. Now, let's look at another function, x cubed plus 2.48x squared minus 4.3155x plus 2.484406. We want to graph this. Notice there are no integers here. This would be very hard to factor and very hard to calculate, like the peaks and the zeros. But let's show how we can do that using your calculator. First of all, turn on the calculator, clear it, and put x cubed plus 2.48 x squared minus 4.3155x plus 2.484406. We want to pick a window like this, minus 5 to plus 3, and then y min, minus 10 to plus 15, graph, and we see this function. And what we want to do now is find out what this 0 is, find out what this peak value is, and what this minimum value is here. We'll do some of these. Notice that here are the answers, and let's first of all turn on our trace, and let's find the maximum value. So let's move the cursor up to the left of the maximum value over here and hit second calc. Maximum It asks you to find the left bound. Well, we've got it on the left, so we hit enter. It asks for a right bound, so move the cursor over. Hit enter, and when it asks for a guess, just hit enter again. And out comes the maximum value, 13.36, which agrees with the graph here, at the value of x equal minus 2.28. If now we wanted to go and find the 0, let's go down here and put it to the left of the 0, hit second calc, hit 0 for the left bound, hit enter, because it's already there. For the right bound, move it to the right, hit enter. And for a guess, hit enter. And it tells you the 0 is minus 3.79. And it doesn't say y is 0 there, but it's very close to 0. So this is the 0. You can do the same thing to find the y-intercept, hit second calc, hit value, put in x equals 0, and you know you're going to get 2.484406 without even calculating it by just looking at the equation. Now, building cubic models from data, this is something we're just going to look at very briefly. Very often, if you have data that looks like it could be a polynomial, in this case, 2 turning points could indicate a cubic polynomial. Sometimes you're given data like this that you can put in your calculator and then ask it to do what we call a cubic regression and give you the best values of A, B, C, and D, which are the coefficients of your polynomial.